In this video, we're going to take a look at some graphs, two types of graphs that are deceiving. So the first type of graph that might be deceiving, that is deceiving, are graphs with non-zero axis. So let's say we have some data that's looking at the proportion, the percent of people that are Republican that believe something, percent of people that are Democrat that believe something, and percent of people that are independent that believe something. For this, let's say we have 48 as a baseline here. And then we have Republican. Maybe it's right there. For the Democrat group, maybe it's up here. And for our independent group, maybe that's right here. And that's something. It tells us something. If this value right up here is 51. And this is pretty misleading because it looks like this bar here, the bar that's associated with the Democrat group, it looks like it's about 3 times as tall as the Republican group. However, if we had an axis that started at 0, so if our axis started at 0, then what we would have is here going up to 51 for the Republican group. That height would be about maybe here for the Democrat group. Going to here, and for that independent group, and when you look at those graphs that have a 0 axis, then those heights are not, it does not make it look like the Democrat portion is more than twice as much as the Republican portion. It looks like it's just a little bit more. And even here, I didn't measure these perfectly. Those were guesstimated. And so it's still distorted a little, but you can see when you start off with a 0 that these heights are more meaningful. I can look at that picture and I'm not like, whoa, there's a huge difference here. I can still see a difference. It's just not the difference has not been magnified. Another way that we might see data that is distorted, a deceiving graph, is when we see pictographs. So when we see a pictograph, those can be misleading. They can be done appropriately. But here, maybe I want to represent my data. I have a value that is twice as much as another value. Okay, so I just want to represent a value that is twice as much as some other value. I want to do this kind of nice. Okay, so here is my 1. I'm going to make that a 3-dimensional cube just so it looks kind of pretty. All right, so that's representing 1. And then I also want to represent something with 2. I'm going to also make that one a cube. This is going to be a cube with a height of 2. So there we have these two cubes. I'm trying to represent that the second data piece, that this here is twice as much as this. But the problem is, once I wrote this as a cube that has a 3-dimensional volume, that volume there for the second cube, that volume is actually 8 cubic units. And the volume for the first object is just 1 cubic unit. And so when I look at these figures, when I look at them as objects, it looks like the second one is 8 times as much as the first one in terms of volume. When we look at the heights are we've only doubled the height, right? So that height is the same, is just doubled. But the volume there was not just doubled. The volume ended up getting multiplied by 8. It's not just 2. And so we have to be really careful about that when we go through pictographs. Pictographs can be done correctly, but we just should be really, really careful. It's not just volumes. You could do something like area instead. And so if I just made this a square instead of a cube, the area of this square here would be 4 units, while the area of this square here would just be 1. Right, so that has an area of 1, while this has an area of 4. And again, that distorts the data. And so we just have to be really careful when we have pictographs. All right, next time we're going to start looking at descriptive statistics. We will see you in our next video.